let's say you have your family and you've got a couple of kids and you decide to put them in private school. Do you think you should still pay for the public school in your area? Even though? So I'll give you an example, like if your property taxes, if you live in a house near this area, okay, if let's say your property taxes are $10,000 a year, okay, let's just say they are. Probably about $6,000 to $7,000 of that is for Northside Independent School District. So think about that, $6,000 to $7,000, $500 a month or so, paying to what? You're not sending your kids to that school, right? What do y'all think about that? Do you think?
Like it's okay because you want the school to be nice, so you want to sell your house. People are like, oh, it's a nice neighborhood, a nice school.
That's true. It's like a return to this.
Okay, so it maintains the value. Okay, haven't heard that argument. I kind of like that one.
They should probably also increase the amount that they tax. Some people have maybe more pricier homes than the other people.
Well, let me just tell you, the response I had yesterday from my college algebra class was almost unanimous, and it was like, if you make more, you pay more.
Yeah.
I mean, that's like if you have money, you have more of the responsibility of paying for everyone else.
Why?
Huh?
Why?
No, I'm telling you what they told me, okay? That's what I'm telling you. I was surprised that was the overall feeling in the classroom, was that.
Commie bullshit.
Well, see, this is why we're going to do math today. This is why we're not going to do that. But very interesting, very interesting. Okay, let's get to math, because we can go way off and we can actually probably upset people. And
YouTube, right?
yeah, I'm recording, but I'm stopping right here. Okay, so look, we were talking last time about continuity, right? At the very end, I introduced the definition. This was the definition of continuity, and it's important, so I'm going to put it over here because I'm going to refer to it. And then we looked at it geometrically. So we'll just review it quickly because it's not going to take long. We basically said a function like this would not be continuous at 2. Why would this function not be continuous at 2? And don't tell me because it has a hole. I want you to tell me in terms of the definition. What fails in this definition? Does the limit exist?
Yes.
The limit at 2 exists. From both the left and the right, you're going to the same place. So the limit, the left side of that definition, is satisfied. What's wrong though? The right side, f of a, is here, f of 2 is undefined. So it's impossible to be continuous at a point if you are undefined at the point. Okay? This one here, well, this limit exists, right? And it is defined at 2, but why is this one not continuous? They're not equal. So even though this exists and this is defined, they aren't the same. There's continuity. That's the continuity at 2 right there. Go into the same place, fill in the hole, we've got continuity. And then what we talked about is basically continuous means you can draw it without picking up your pencil, right? And then we said anywhere where you're not continuous, we will say that the function is discontinuous, all right? And I said the types of discontinuities we could have are jumps. Anywhere you have a jump or a break in the graph, you're going to be discontinuous. Anywhere you have a vertical asymptote, this is called an infinite discontinuity. And then anywhere where you have a hole, you're going to have a discontinuity, and this is called a removable. Why was it called removable?
You can move those.
Yeah, it's kind of the idea is that this would be easy to remove the discontinuity. It would be very easy for us to fix this. We just fill it in and we'd be done. Okay, so now we proceed. All right, so this is the new stuff. With continuity, we have 2 new sort of notions, and the notions of a function being continuous from the left and a function being continuous from the right. And the notation we use for it is, all we do is we change this definition just slightly. If we want to talk about continuity from the left, then we only are looking at the limit as we approach the value of a, or whatever the number is, from the left. And if we want to talk about continuity from the right, then we're going to be approaching the number from the right. So we put a little plus. And I have a visual representation. Okay, so look at this right here. Is this function continuous at 2? No, it's not, right? It's not continuous at 2. Why? There's a jump, right? There you go. You have a jump to discontinuity. Now, is it left continuous at 2? So if I go here to 2, and I ignore this side of the graph, do I have a left-hand limit? Is it headed somewhere? Yes. Is it headed to what the function is defined to be there?
Yes.
Yes, so that is left continuous. Is it right continuous? It is not right continuous because even though the limit exists, right, I'm going somewhere, it's not filled in, okay? That makes sense visually? So that's left continuous, not right continuous. And that one right there would be right continuous, but not left continuous. At 2. At 2. Okay, so with that idea, we now move on and talk about continuity of a function on an interval. So up to this point, we've talked about, you know, is a function continuous at a point, right? Just at a single point. And we look left and right, fill in the hole, right? But now we say, can we talk about continuity on a whole interval? That means every point inside. So take a look at that function right there. If I pick any number between 1 and, that looks like 3 here, okay? If I were to pick some value like here, 2, is it continuous at 2? Yes, the limit from both sides, it's filled in. If I pick some number over here, is that continuous there? And just by looking, you can tell that at every point in here, right, it's continuous. Now, what about at the left endpoint at 1? Is it continuous at 1? No. Why? Because you don't have a left side, right? So at 1, it's not continuous, but it is right continuous. Yes? And then what about at 3? Are we continuous at 3?
No.
No. Are we right continuous?
Yeah. No.
No. Are we left continuous? Yes. Right? So when we look at an interval, see in this interval we're talking about the interval 1, 3, right? If we want to say that a function is continuous on this interval, right? If we want to use that wording, say, hey, look, I've got this function, it's continuous on this whole interval, then what we need is that it's continuous everywhere inside, okay? So on this, on the inside, it's got to be continuous at every point. But what about the endpoints? What do you think the condition will be for the endpoints? So to say it's continuous on the whole interval, we need it to be continuous everywhere inside. And then what do you think the condition is for the left endpoint? We have to be what? Right continuous. And then at the right endpoint, we would need to be left continuous. So to talk about continuity on a whole interval, you need continuity at every point inside, and you need right continuity here and left continuity here. Now I summarize that in Word in the notes here. So it says given, nope. Here we go. A function f is said to be continuous on an interval if it is continuous at every point in the interval, okay? At the left endpoint, the function only needs to be right continuous, and at the right endpoint, the function only needs to be left continuous. All right? All right, moving along. These ideas are pretty visual, so most students have pretty easy time with this in terms of understanding what's going on. This is a theorem about combining continuous functions. So this is what it says. Given two functions, f and g. So imagine you have a drawing, right? F, you have another drawing, there's g. And let's say they're both continuous, all right? And let's say you're given some constant c. So c is like just some number. And you're given some point x equals a. All right, so we have two functions. Here's f. I don't know, g does something else, whatever. And we're looking at point a. And so we've got these two functions, right? Then here's what we can say. If we add or subtract the two functions, you will still have a continuous function. All right, so adding two continuous functions together or subtracting two continuous functions together are guaranteed to still maintain the continuity at the point. All right, and this is a theorem, which means you're just going to say, okay, I accept. All right, we're not going to go through and prove it. So adding and subtracting two continuous functions results in a continuous function. Multiplying a continuous function by a number will still result in a continuous function. So I'll give you a more concrete example of that. Let's say I have the function f of x equals sine x. Do y'all believe that sine x is continuous everywhere? I mean, just think about the picture, right? No jumps, no breaks. You can draw it without picking up a pencil. So if you believe that that's continuous, then what do you think happens if I take that and I multiply it by 3? If I just multiply it by a constant out front? Do you think that changes the continuity? I mean, it changes the picture, but does it change the fact that you can draw it without picking up your pencil? No, it doesn't. And that's what this theorem is saying. Start out continuous, multiply by a number, you're still continuous. Start out with two continuous functions, add or subtract, you're still continuous. How about multiplying and dividing? What do you think? Yeah, we're good. If we multiply two continuous functions, you still get a continuous function. If you divide two continuous functions, you still have a continuous function, but there's one little caveat to that, and that is you have to be careful that the denominator is never 0, because if the denominator is ever 0, then you're obviously going to have a problem, right? Because your function won't even be defined. So products are good, quotients are good with the exception of the denominator being 0. Okay, so let's see. What do you think comes next? I'm saying if we have two functions we add or subtract, still continuous. If we take two functions, multiply them, still continuous. We divide them, still continuous. Squared. Okay, so squared would be like multiplying it times itself, right? So that would still qualify, right? So that's kind of covered here. What's the operation I haven't talked about? The thing you can only do with functions. You can't do them with numbers. Composition. So what do you think? If I have a continuous function and I place it into a continuous function, like let's say I take sine x, no, not x, sine of, let's say, like x squared plus 1. This is composition, right? This function right here, x squared plus 1, is a parabola, right? You can draw that without picking up your pencil. So that's continuous. If I take that continuous function and I plug it into sine, which we said was continuous, do you think you're still continuous? Yes, and you are. But there's a theorem that tells us that's true. So that's the next thing. Where is it? Down here. Theorem. Composition of continuous functions. So if g is continuous and f is continuous, then you can plug g into f and you can still maintain the continuity. All right? So these are all things now we just are going to accept, and as we move on, if we're ever dealing with a function down the road and we're like, hey, is it continuous? We're just going to say, yeah, because this theorem back here. All right? All right, now, there is a whole slew of functions that you've studied in your life, right? Lines, parabolas, polynomials, rational functions, exponential functions, log functions, trig functions, right? So we can summarize right now which of those are continuous and which aren't. So here's the summary right here. All polynomial functions are continuous where? Everywhere, okay? That means a line is a polynomial, right? You can draw a line without picking up your pencil. Both directions forever. Parabola is a polynomial, right? Draw it without picking up your pencil. Both directions forever. Cubic function does something like that. That you can draw without picking up your pencil. Every polynomial out there is continuous. Everywhere. How about rational functions? Rational functions are a little bit tricky because rational functions are like here's an example of a rational function. We've looked at that one as one of the very important famous ones, I guess. Right? That's 1 over x. There's obviously a problem with that. I cannot draw that without picking up my pencil. Do you agree? But this is saying that it's continuous what? As long as you're looking within its implied domain. So 0 is not in the domain, right? So as long as I'm to the left of 0, I can draw it without picking up my pencil. As long as I'm to the right of 0, I can draw it without picking up my pencil. So it's continuous here, and it's continuous here, so it's continuous on its implied domain. Do you see the kind of difference between that and the one before? Okay, what about trig functions? Sine, continuous everywhere. Cosine, continuous everywhere. Tangent. No, because tangent is periodic, right? But it's continuous on its domain. So when you do draw that tangent function, right, tangent has these vertical asymptotes like that at negative pi over 2 and pi over 2, and then it just repeats itself, doesn't it? Just keeps doing that. Okay, so as long as you're within one of these little sections, when you're drawing it, you can draw it without picking up your pencil. And that works for all the trig functions. Secant, cosecant, cotangent. All of those curves, when you draw them, they're continuous on their implied domains. And lastly, all exponential and log functions are continuous on their implied domains. Exponential, I think that's easy, right, to agree that when you draw an exponential function, you don't have to pick up your pencil. Logs, same thing, but logs do have domain issues, right? You can't plug a negative into a log, can't plug 0 into a log, so as long as you're within the domain, when you draw it, you're good. All right. So what are we going to do with this? Do you see why I did all the limits and then ended with this kind of? It would have been weird to go talk about all this and then go back and do more limits. It just seems not as natural to me. These are just pictures. Do you really? You don't need to see these, right? This is. I was going to give you. See, you can draw it without picking up your pencil. No. Composition. Oh, here's composition. I think this one's kind of cool to look at. See that function there? In case you can't read it up there, that's the function sine of x squared minus x. So you can see that that's a polynomial, right? That's continuous. You're plugging that into a continuous function because it's a trig function, sine function. So when we put those together, the graph of that you should be able to draw without picking up your pencil. And there's the graph. Kind of cool looking. All right, how about this next one? E to the cosine x. When I graph that, that should be a nice continuous function. There it is. Kind of an interesting looking function, huh? It's like waves. Okay, what about this next one? Natural log of x over x squared plus 1. Now we do have a little bit of an issue here. This in here, is that a continuous function? It's a rational function, so it's continuous on its implied domain. What's the implied domain of this? Are there any numbers you can't plug in? Forget the log right now. Are there any numbers you can't plug into this that would cause a problem? Now, you can plug 0 in.
You can't plug anything less than 0.
Okay, but I'm saying ignore the log right now. Ignore the log. Just in terms of a rational function, in terms of this by itself, are there any numbers that would cause a problem with that division? Can you ever make the denominator 0? No, you can't, right? Unless you bring imaginary numbers in, but we're not allowed, right? So this right here is a continuous function everywhere. There's no domain restrictions on that, right? Does everyone see that? Okay. However, when you plug it into the log function, now you have issues. Because now you have to promise me that this won't ever be negative and this won't ever be 0. So when I go to graph this, wherever it does draw a graph, it will be a continuous graph. But there are some domain issues. So there it is. There's the graph. All that for that little graph right there. Okay, so there's the graph. And then the last one here, well, there's two more. That's a cool one. That function right there is the function square root of x squared plus x minus 2. So inside is a polynomial that's continuous. The square root function is continuous on its implied domain. There are domain issues. You can't have negatives under here. So anywhere where this parabola is negative, you wouldn't have a picture. So there's the picture of the composition, but you know, this part at least I can draw without picking up my pencil. And finally, tangent of sine x. That's That's what it is. That's tangent of sine x. Okay. Fun with pictures. And now we get to the almighty intermediate value theorem. One of the most important theorems in math. Its importance, the importance of this theorem I can't express to you very well because you won't ever really appreciate this theorem. You've used it many times, okay? But you can't really appreciate it unless you really ever have to go like prove theorems. So if you're a math major, you'll use this theorem a lot, okay? It's one of the foundational theorems. And I said you've already used it. So let me kind of show you how you've used this before. Do you remember somewhere in like a college algebra class or something like that where maybe you had some polynomial function? This would be college algebra, all right? And I'm totally making this function up. I have no idea what this looks like, okay? Let's say you would go and you were asked to draw a sketch of this in college algebra. You would figure out what the left and right behavior of this was first. So you would figure out that like the left side goes down, the right side goes up, and you could tell that by looking at the leading coefficient and the power. Does that ring a bell?
Yes.
Okay. And then the next thing you probably did was tried to factor this or set it equal to 0 and tried to find the x-intercepts. Okay? So maybe you would find out like you have an x-intercept. I'm just going to make this up. Let's say you have those x-intercepts. And you know that like maybe the left side goes down, right? And the right side goes up. And then what you would do is to figure out if this thing did like this or if it like bounced off and came like that. One way is you could use the multiplicity thing, but then you could also just do a test point, right? You could just like test a point, just plug it in and see if it comes out to be up here or down here. So this idea of test points, y'all have used this before? You test a point. Let's say we test that point and it pops out right here. Then what we told ourselves is, okay, from here to here, right? We had a point here, so that must go like that, right? Okay. What guaranteed you, whatever told you that this thing couldn't, have done this and then gone back up there and done that? Like, why?
Because there's no more x-intercepts.
Why not?
Because that's what we would have taught. Because we're going to test the
Because you think you've found them, right? Right? You've found them. So I would agree. The x-intercepts should dictate that, right? But when we do test points, we are assuming that our function doesn't do this. Look, what if our function does this? Okay, I'm going to draw you a function right now that has this x-intercept and this x-intercept and the test point that gives you that, but I'm going to make it appear down here also. So here it goes. Ready? So here it comes up like this. It's going to go up to here, and then right there, it's going to all of a sudden magically come over here and appear and come like that. Does that function have these two x-intercepts still? Yes? Does your test point plug in up here? Yes? Okay. Did your graph have to stay up here? Does it look like it always stayed up here? It didn't, right? I made it go like this. Yes? So why in college algebra were you not worried about this happening? That it would all of a sudden, like, the graph would like disappear and show up on the other side.
Then we check the y-intercepts.
Yeah, we could check the y-intercept, but I'm saying why in college algebra did you know that if these were two x-intercepts and that test point came out to be this, that you would have to draw your little hump like this? Why weren't you ever taught to think like this could happen? Because that's a perfectly defined function, isn't it? So why weren't you ever looking at that? Because they already knew in college algebra, they didn't talk about it, but this is a continuous function, right? This is continuous. This is a polynomial. Polynomials can't do this. Why? Because this is a discontinuity. And polynomials can't have discontinuities because they are, well, continuous everywhere, right? So this sort of weird, wacky behavior does not happen with polynomials. So we didn't have to think about it. But now I'm telling you, look, I mean, if I were to just come into class right now, and I were to say, hey, everyone, x-intercept here, I have a function. X-intercept here, and this point here. Draw me the function. Most people are going to do this. They're going to draw that and they're going to do that, right? And then my next question would be, does your graph, can it ever be down here? And most of you are going to say no. Because you're assuming it's continuous. But if it's not, I can make it do weird things. Are y'all following me or not? Okay. So the intermediate value theorem establishes basically the principle that you were using in college algebra when you weren't even thinking about it. It establishes that your function's not going to act crazy. Okay, so let's look at what the intermediate value theorem says. Let me read it first, because it's pretty ugly to read. Suppose f is a continuous function on a closed interval ab. So you've got some function that you can draw between two endpoints, right? Where the two endpoints aren't the same. F of A and f of B are not the same. Let n be any number between f of A and f of B. Then there exists a number c in the interval ab such that f of c equals n. I mean, that's obvious, right? Okay, so here's what this theorem is saying. All right. Suppose we have, this is so key, suppose we have a continuous function, which means when we draw it, we don't get to pick up our pencil, right? Okay, so here, do we have a continuous function? All right, let's restrict that function to a closed interval. Boom. Okay, so now it's on a closed interval, right? So I'm going to scroll back up to the theorem. Suppose you have a function you can draw without picking up your pencil, and that it's on a closed interval AB. Got that? Okay, what does the next part of the theorem say? We need to make sure that f of A and f of B aren't the same, which means that the height at this endpoint and the height at this endpoint are not the same. Right? So do you all agree that this at this left endpoint, this y value is not the same as this y value? Okay, so we've satisfied the third condition of this theorem. Continuity, right, is the first condition. Closed interval is the second condition. Third condition is endpoints don't match. So what does it say happens? Well, let n be any number between f of A and f of B. Let n be any number you want, okay? So let me pick an n. Here, this was checking to make sure they're not the same, the endpoints. So let's choose any number between, so right here, do you see this is the height of one of the endpoints, this is the height of the other endpoint, right? So I'm just going to scramble. Someone tell me when to stop here. Right there? Okay. So we just let n be any number between those two. Agreed? The theorem says then, there must exist, there has to exist, a number c somewhere in the interval AB. So there's got to be a number between here and here. So the interval we're looking at is from A to B. There must be some number in here such that when we plug that number into the function, it's going to spit out the height of that red dot. So there must exist somewhere in here. So this is the height of our function, right? Somewhere in here, that height comes from some value c within the interval. And that would work for any n you pick. So if I pick an n over here, there's got to be some value that I plug into the function that will take me there. So the theorem is saying that if you pick any value between here, right? Here and here, there's got to be some x coordinate that gets mapped to that, right? Any value between here and here. Like any intermediate value between here and here. The intermediate value theorem, that's why they call it that. Now, why is this important? Why in the world is this an important concept? Let's do this. Take a look at this problem right here. I'm going to let you just sit there and look at it for 30 seconds. Use the intermediate value theorem to show that this equation has a solution somewhere between 0 and 1. All right. See this equation? That's an equation, right? Let's try and solve the equation. I'll put it over here. I'm going to call on some poor soul here. Now, I have my sticks separated. Some of you got called last time, some of you didn't. So let's see. Jasmine? Jasmine? You got called last time? No. So you're in this group. David Garza? Didn't get called last time? You got called last time? Herman? You got called last time? Sure you didn't get called last time?
I wasn't here.
Oh, you're in that absent group. Oh, what are you doing over here? Over here, what happened there? We'll put you in there. Okay. So here. So this is going to be an unlucky soul here. Jesse. Jesse E. I didn't call you last time, right? Okay, just make sure we're... Okay, Jesse. I'm calling you unlucky because I'm asking to see what you think about solving that equation. Any ideas? You're asked to solve for x, right? I want you to tell me what x is. Just the 3 letters COS? Can't. Because COS is not like a number. It's a function. This is cosine of x. So you can't, you could divide by cosine of x, but you can't just divide out COS. Okay, so if I divide cosine x on this side by cosine x, and then I have x over cosine x, and then that becomes 1 equals x over cosine x. Okay, but I don't have x by itself yet, right? Yeah, this is torture, actually. Sorry, you got called. Anyone have any ideas on how to solve this for x? How about arc cosine? Inverse cosine. Doesn't inverse cosine kill off cosine? Okay, so let's try that. All right, maybe that'll work. So if we do arc cosine over here of cosine, and then whatever we do one side, we have to do the other, right? So this side becomes what? X. Okay, we were solving for x, weren't we? And then this side is what? Arc cosine of x. And why is that still not good? Because in order to know what x is, you actually need to know what x is, right? We had that same problem up here, right? Like if you want to know what x is, then you got to tell me what x is. So is there a way to solve this equation? There is not, okay? There's no way to solve this equation. We never learned it. I mean, you're never going to learn it, okay? There's not going to be a method that you can do. Now, you can do numerical. There's a numerical way of doing it, but even with that, you're going to be using some sort of what we call infinite series or something like that. And so there's numerical ways of doing it, but there's not a nice closed form like in algebra where you like factored or square rooted both sides. Doesn't exist. Doesn't exist. But we're still being asked to show that there is an answer. There is a solution to this. Okay? And we're being asked to show that there's a solution in here. Now, look at the wording here. Use the intermediate value theorem to show that this equation has a solution in here, but don't go and try and find the solution. Just prove to me that it exists. Prove to me that it exists. So here's how I'm going to prove it. All right? What I'm going to do first is I'm going to take this equation and I'm going to move everything to one side. Okay, do you all agree that that is an equation still? Same equation? And now what I'm going to do is on the left side of this equation, I'm going to define the left side of that equation to be f of x. So I'm creating a new function called f of x, which is cosine x minus x. All right? Now, when I do this, what does this geometrically correspond to? Whenever you're in any math class and you've ever set a function equal to 0, you've done that when you've been trying to go and find the what? The x-intercepts, right? Do you agree? So to say, hey, look, solve this equation means solve this equation, but if I call this side f, then I'm really saying find the x-intercepts of f, right? That's what this is really saying. Find the x-intercepts of that function right there, this one. Now, is there anything you can tell me about that function? Is there anything you can tell me about that function? F of x equals cosine x. In terms of what we've learned today, is there anything you can tell me about that function? It's what? It's continuous. Why is it continuous? Cosine is continuous. X by itself is continuous. And when you subtract two continuous functions, it's still continuous. So this is a continuous function, right? I'm trying to get us to show that there's some x-intercept to this, somewhere between 0 and 1, right? So let's look at this function on a closed interval. On the interval 0, 1, right? This function is defined, right? Do you see that we're starting to satisfy the criteria for the intermediate value theorem? We have a continuous function on a closed interval, right? What we need to figure out now is, do the endpoints, are they different? Is the value of the function different at the two endpoints? So let's check. Oya? Oya. Oya? O-Y-A. Oya? No? No, Oya. I can't read this. Oh, wait, this is Sienna? Sienna. 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 So what is, I said, let's check to make sure the two endpoints don't give us the same value, right? So what is our function at the left endpoint? What's f of 0? So cosine of 0 is 1, and then minus 0, right? So we get 1. Y'all agree? Okay, so at the left endpoint I have 1. Let me kind of draw a picture of what we've got here. This function, right? This function, what I can say right now is that at 0, I'm at 1. Okay, let's check the next endpoint, f of 1. So this is cosine of 1 minus 1. Now, unfortunately, no one in here is going to know what cosine of 1 is, because you shouldn't know what cosine of 1 is. So we actually need a calculator to do this. So somebody on their calculator, make sure you're in what mode? Degree or radian? Radian mode, because these are numbers. These are not, they're not giving you angles in degrees, right? So in radian mode, type in cosine 1 minus 0 and see what you get. What do you get? Oh, sorry, I thought you... Negative 0.45. Okay? Negative 0.45. So that means when I go out to 1, where's the dot? Somewhere below, right? So have we satisfied the third condition for the intermediate value theorem? Continuous function, closed interval. Do our endpoints match? No, that's good, right? We don't want these to be the same answer. This is a number, this is a different number, right? So we have all the conditions satisfied, right? Now, who cares? Who cares? How is this going to answer the original question? Does anyone see why we now can conclude this? Yes?
In order to connect them, it has to pass through the x-axis.
That's it. In order to connect these two together, you have to go through the x-axis, don't you? Right? You have to. And you can't pick up your pencil because it's continuous. So even though you don't know exactly what it looks like, you know you got to get from here to here and you can't pick up. So the intermediate value theorem says, look, at this point, every value between negative 0.45 and 1, every value between here and here has something that gets mapped to it. So the value we are interested in is what? What value were we interested in this function being? 0, right? So 0 is between here and here, right? It's actually here. So when I graph this, somewhere between 0 and 1, right? Somewhere between 0 and 1, we have to have a c, an x coordinate that would spit out 0. Does this give us the answer, though? Does this give us the answer? No, it doesn't. It just tells us that it lives there, right? Somewhere between 0 and 1, the answer is there. That's impressive, no? No, you're not impressed. I can tell you're not impressed. And I would understand why that's not impressive. Because it doesn't give you the answer, right? Agree? Doesn't give you the answer? Just tells you it's there? That doesn't help, does it? Okay, so here's what I'm going to do now. I'm going to go to Wolfram alpha. Y'all heard of Wolfram alpha before? Yes or no?
Yes.
Okay, Wolfram alpha. There's many other math programs out there. But what I'm going to do is I'm going to type into Wolfram alpha the equation we're trying to solve.
Isn't it that it's a good idea to know this, because that way if you try to pick an interval or any value between 0 and 1, you're actually narrowing your possible results to actually pick from?
You are narrowing them between 0 and 1, but how many numbers are between 0 and 1? An infinite number of them, right?
Right.
So I agree, you have narrowed it down, but you've gone from infinite to still infinite, right? But you're dead on exactly right. That's the road I'm about to go down. Hold on, though. I typed this into Wolfram alpha. I don't think I hit enter. I hit enter. And then coming down here, blah, 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 blah. It plotted it. Look, it drew the graph for me. But where's the answer? There it is. Okay. What is this saying? This computer is saying x is what? Approximately squiggly equals, right? Is like kind of like close to 0.739085. Okay. Now, did it say anywhere here, like, that it couldn't solve that? Yeah, I don't think it says how it solved it. So Wolfram alpha just must be smarter than everyone, right? It's got like magicians back there solving equations. So how did the computer solve the equation? Your computer uses the intermediate value theorem. Now, but I just said the intermediate value theorem doesn't give you an answer, right? So imagine you're a computer, if you will, for a second. The only thing you're good at is arithmetic, right? That's the only thing you're good at. You can do arithmetic and you can do it very fast. Yeah? Okay, so if I were going to program a computer at this point to try and find this solution, right? Here's what I would do. See if you follow this. I type this into a computer, right? I type this into a computer, say solve. The program that I write is going to do this. It's going to look at that expression. It's going to pick two arbitrary points out of the air, 2 points. It's going to plug those 2 points into this function. So imagine the computer is going to pick two endpoints arbitrarily. It's going to plug A into that function. It's going to plug B into that function. And what it's going to hope for is that one of these is positive and the other one is negative. Kind of like we got here, right? Because so it picks the 2 points, plugs them in. That it can do very fast. It can look at these two answers and it can check whether or not they're opposite in sign, right? Do I have a change in sign? If it does, then what it does is, what do you think it does?
Continue to do that closer and closer.
How though? How does it continue to do that?
Just pick signs in between those. Pick numbers in between those.
Exactly. So right now the computer knows this. Between A and B, right? My graph goes through here somewhere, right? It kind of knows that because it changed from a positive to a negative. So what it'll do now is it'll cut this in half. It'll bisect that interval. So let's call that C. And then what the computer does is it checks between A and C now. And what is the computer going to see when it checks between A and C? It goes from positive to what? Positive. So it says, it didn't happen there. Checks from C to B, it goes from positive to negative. So it says, it's in there. So then what does it do? Cuts that in half. And then it does it again. And it keeps on bisecting down. And sometimes it'll go to the left one, sometimes to the right. It just depends. And eventually, it gets to a point. Now, does it ever get there? It never actually gets to the point because there's an infinite number of points. But built into the code, every single time it runs through the loop, at the last step, it takes the difference of these two numbers. So let's say that number was 0 and this number was 1. It says, I went from positive to negative. Yes, I have an answer in there, but the difference between these two numbers is 1. And that's too big. So it does the algorithm again, and it'll stop. The program will stop when the difference between these two numbers is some predetermined amount. Maybe the difference between those numbers is like 0.0000000000000001. And that basically means you've found it. And that's why you have a squiggly equals here. Because it didn't find it exactly, it found it within a certain tolerance. So it's an acceptable answer. Does that make sense? That's called the bisection method for finding roots of functions. Now that method is not the one that Wolfram Alpha used. That's the most primitive form of finding roots. I guarantee you Wolfram Alpha used a much more complicated algorithm, which we'll actually see one later. I'll show you, called Newton's method. It's a way that you can find roots in it. The thing is, what it does is it gets to the answer faster. So in terms of operation counts on the computer, it makes it less. So in computer science, anyone ever heard of this before? Big O? Big O is like operation count, basically. It's like whether or not it's, well, we won't get into it. Never mind. All right, so the intermediate value theorem. Super critical. Used all the time. But it's pretty basic idea. I mean, if your function is continuous and it goes from positive to negative, you got to have a zero somewhere in there. All right, how are we doing? 148. We have one more problem to do and we'll be done with this section. Sorry, I've got to look at my code here real quick and get the function that I'm going to mess with right now. Let me just jot it down over here. F of x is x squared minus 4 over x minus 2. If x is less than 2, ax squared plus bx plus 3. If x is between 2 and 3, and then 2x minus a plus b. If x is... Okay. All right, so here we go. I can write it down over here now. All right, so I'm about to define a function. I wrote it down over there, but I'm going to write it down again. And the function is a piecewise function. So this function has three pieces to it. The first piece is x squared minus 4 over x minus 2. And it is going to be that function so long as x is just less than 2. And then the middle piece is ax squared plus bx plus 3, as long as x is bigger than or equal to 2, less than 3. And then finally, 2x minus a plus b if x is greater than or equal to 3. Okay, so just jot that down, and then we'll talk about it. I'm going to leave that. I'm about to use it. All right. So this first piece of this piecewise function, x squared minus 4 over x minus 2, that is a rational function, right? And so it's continuous on its implied domain. And its implied domain is basically everything except 2. And we are supposed to draw this function only to the left of 2. So this right here is this red piece, right? That's this red piece over here. This is part of some rational function. Now what about the middle piece right here? What type of function is that? So this is the red one. That's a polynomial, right? It's actually a quadratic, right? It's quadratic. But I've put a and b in here, which means that I'm not telling you what a and b are. Yes?
Sir, on the second, where you have x is less, correction, greater at 2.
Oh yeah, ignore that. I had to look at this before I could determine it from here. Yeah, don't worry about that. Yeah. So this is a parabola, right? But if I change a and b, it's going to change the shape of the parabola. Okay? And this is what? A line, right? And if I change a and b, it's going to change where the line is, isn't it? So I'm supposed to draw the rational function to the left of 2, this parabola between 2 and 3, that's the blue one, and then I'm supposed to draw this line to the right of 3. So that's what I have the computer's done that for us. Now right now I have the ability to change A and B. So right now what you're looking at, A is 0.65 and B is 1. All right? Is this a continuous function? No. What would I need to do to make this continuous? I would need to somehow move these together, right? So see, I'm adjusting A, and it's changing the shape of the blue piece because A affects the leading coefficient, right? But then A also affects this line. So as I change A, it's going to move the blue one, but it's also going to change the gray one a little bit, isn't it? And then if I change B, is it going to change the blue one? And the grayish one, right? So that one's changing. So what I need to try and do is see if I can't find a way to make them, you see what I'm trying to do? Like I'm trying to make these match so that I could draw it without picking up my pencil. So there's the piecewise function, here are the instructions. Find A and B such that f is continuous everywhere. So you need to tell me exactly what A and B have to be in order to plug them in, plug whatever A and B are here, A and B here, and when you're done, it should draw this and you should not have to pick up your pencil to draw it. All right? So how do you think we're going to go about that? How are we going to go about doing this? We might need it at some point. So can you tell me, just by looking at this right now, is our function continuous to the left of 2? Okay. Is it continuous between 2 and 3? Yes? Is it continuous past 3? Yes. And the reason why is because as long as I'm to the left of 2, I'm a rational function, and those are continuous on their implied domains. If I'm between 2 and 3, I'm a polynomial, and polynomials are continuous everywhere. This is a line, it's continuous everywhere. The problem is I have to somehow paste them all together to make an overall continuous function. So where are the only 2 places that I have issues? Where are the 2 places where my continuity is breaking down right now? At 2 and at 3. Right? At x equals 2 and at x equals 3, we need continuity. Agreed? Okay, so because that's what I need, I'm going to write that down. We want, or we need, let's need sound stronger. We need continuity at x equals 2 and x equals 3. All right, let's start with x equals 2. So continuity at x equals 2 is where we will begin this. Salo. No? Is that Salo? Right? I said that perfect, right? Yeah. Perfect. Salo. What is... I'm going to let you write it. Take a breath. What is the limit definition of continuity of a function at 2? If I tell you that a function needs to be continuous at 2, what does that mean in terms of the definition of continuity. And I'm not talking about visually, I'm talking about the precise limit definition. Okay, so but at 2, we want it at 2. So saying that we want continuity at 2 means that we need to write down the limit, right, as x approaches what? 2 of the function must be equal to f of 2. Perfect, okay? So we need it to be continuous at 2, right? So we're going to write down the definition. This is what we need. We need the limit as x approaches 2 of our function to be equal to f of 2. Perfect. Right? That's what we need. In order for this thing to paste together at 2, we need that limit to hold. Agreed? All right. I have no good markers. Arturo.
Yep.
Where are you at? Okay, Arturo. Arturo, if I need these to be true, okay, I need the left side and right side to be equal in order for this to be continuous at 2. I'll let you do the easier of the two sides. What is f of 2? So look at your function. If I tell you to plug 2 in for x, which of the 3 do you go into? The top, the middle, or the bottom? The middle, right? And then you go in the middle because that little symbol right there, right? That symbol right there means you're going to let x go in here. So replace x with 2 there and tell me what you would get. Place x with 2 here.
Oh, a of 2 squared plus b.
A times 2 squared, so 4a
Yeah.
plus b times 2, which is 2b, plus 3, right? So the right side of this needs to be 4a plus 2b plus 3. Does everyone follow that? In order to be continuous at 2, you need the right side of this equation to be this. Now, whoever gets picked next gets the harder part. James? I didn't go looking for it. It was right there. Okay, James. You get the left side, right? Now, everyone pay attention to this left side, because what in my experience of teaching this, okay, and trying to explain it to students always think they're doing it right, but a lot of times they're not, okay? So pay attention to this step right here, because this is how you'll either get the points or not get the points on the test. Right now, we're going to take the limit. We need the limit as x approaches 2 of our function to be equal to f of 2. We know f of 2 is this. So when we're taking the limit here as x approaches 2 of the function, what function? Like, our function has 3 pieces. So which of the 3 pieces is it? Is it just one of them, or like 2 of them, or is it all of them? What is this?
Again, it's wherever that limit holds true at the red one.
Okay, it is the red one. Why though? Let's make sure we all understand why it's the red one.
Because it's going to, yeah.
It's approaching 2, right? That means we're not 2, right? This is what we're doing when we're at 2, right? And that's not interesting to us. In fact, if I ask you to take the limit right now as x approaches 2 of this, you would just replace that with 2 and 2, and you would get 4a plus 2b plus 3 equals 4a plus 2b plus 3. Who cares? 1 equals 1. Who cares? That doesn't help you, right? But here, your x is smaller than 2, but that means you can approach it, right? So which side would you be approaching 2 from there? Left side, right? So I'm going to write limit as x approaches 2 from the left of the x squared minus 4 over x minus 2. All right. Now, shall I move on, or you want to go after that limit? Okay, how would you handle it? Does everyone see that we now have a limit that we have to calculate? Okay, we're going to, pardon? Where's this coming from? This, okay, so let me bring the graph back up. So we have a problem at 2, don't we? We have a problem at 2? Now, at 2, we were defined to be this point. We are going to come in and try and paste the red one to the blue one, so we are going to approach from this side. And that's why we're going to use this function. Okay? So we're trying to make our limit from the left match up to the point